In this video, we are going to learn about confidence intervals. Let's use the example we used in the previous video for p-value and hypothesis testing. In this study, we are comparing effective intervention to control group and on the outcome of days of life without ventilation. We call it ventilator-free days. And we are looking at patient in ICU. So let's see how they report. They reported that control group and intervention group have 3.1 day difference in terms of ventilation-free days. And the p-value for that difference is 0.02. So we know since p is less than 0.05, so this indicates there is statistical difference in ventilator-free days between the groups. And today, we look at 95% confidence interval. So 95% confidence interval they reported is 0.7 to 5.6 days. That corresponds to mean difference of 3.1 days. And third, here is the utility of confidence interval. If the confidence interval excludes the null value, okay? In this case, null value is 0, right? If the two groups are not different, and then difference would be 0. And so if the confidence interval exclude, and this corresponds to p less than 0.05. So by looking at confidence interval, and you don't really have to look at the p-value because you know p should be less than 0.05. So you can use confidence interval to judge if there is statistical difference between the two groups. Okay. So let's look at another example. And another outcome they look in this study is percent of death. And so they compare mortality between two groups. And they say intervention group had 32% less likely to die compared to control group. So hazard ratio in the Cox regression they use is 0.68. Okay? And this was statistically significant. And then again, 95% confidence interval. In this case, let's see if it's excluded the null value or not. If you think it's significant because it's excluded 0, then you are wrong, because we are now looking at the ratio, right? So for ratio, the null value is not 0, it has to be 1. So the result, in fact, is the same, though, but the reasoning is different. And so this confidence interval excludes 1, therefore, p-value must be less than 0.05. So it provides statistical evidence to indicate difference between the two groups. So this is how we use confidence interval. That's easy, isn't it? So if someone asks you, well, explain the meaning of confidence interval, how do you explain it? And this is what many people actually explain confidence interval. There is a 95% chance that the population parameter, i.e. true difference, lies within this interval. So therefore, since this interval doesn't include 1, the null value, so 95% of times difference is less than, the ratio difference is less than 1, and therefore it's statistically significant. And that's how many people explain confidence interval. And in fact, for statistician's point of view, what I just say is wrong. And the correct way, okay, so let me read this. If we took repeated samples and computed the 95% confidence interval for each sample, then the true parameter would lie within 95% of those intervals. Well, it sounds similar to what we just said in here, right? But it's obviously different. Okay. So let me say it again. If we repeatedly take samples and computed the 95% confidence interval for each sample, and then the true parameter would lie within 95% of times within that intervals. Okay. And so let me use a figure to explain what I meant. All right. So this is the simulated data, and this is a computer simulation. So we randomly pull n equal the same sample size to this study. So that's 365 patients' data. Okay, so we randomly pull 365 observations from random number generator, and then which has true parameter of 2.7. Okay, and so here is a mean. This is a mean of 365 draws. This is another mean of another 365 draws. This is another mean of another 365 draws. Okay. And here is what we observed. So what we observed in this study is difference of 3.1 days. And again, our study is one of many studies, right? And we could publish in Lancet because we were the first one to study, but there would be many people who could study similar things. So assume there are 20 similar studies and each use the same sample size, and then they randomly pick the patient and then computed confidence interval for their mean difference. Okay. And this is ours. So by looking at this, what you may have already realized is, what does randomly fluctuating here? Is that true difference or random samples? Which is random samples. So what the randomly fluctuating is each sample mean, and our data just happened to be one of them. Okay. And so a critical difference between this interpretation and this interpretation. And this interpretation we assume as population parameters are randomly distributed. So there is 95% chance to fall within 95% confidence interval range, which is wrong because what actually fluctuating randomly is not the population parameter. It is a parameter from each random samples. Okay. So what this is say is population mean is it doesn't fluctuate, but if we randomly draw many samples and 95% of time these true parameters are captured. So here we have 20 and then only one random sample exclude the true parameter. So it is 19 over 20 and 95% of times, and these interval capture true population parameter. And since I'm a statistician, I had to emphasize on this. Although when you actually report confidence interval, no one really use this way to explain confidence interval. So as long as if you know utility, how to use confidence interval, I think it's okay. This is how you use confidence interval, and we already talked about it, so this will provide a summary. So what you have to check first is what is the new value. So if you're using student t-test, ANOVA, and linear regression, and it compares absolute difference. So new value would be 0. Although if you're using logistic regression, Cox regression, or risk regression, and you're looking at the ratio, so the new value would be 1. Okay. And then after you know what's the new value, and you check if the confidence interval includes the new value. And if it's include, then corresponding p-value would be less than 0.05. And if the confidence interval exclude, this is typo, sorry. And then p-value would be less than 0.05. And actually the equal sign should come here. And when the p-value is exactly 0.05 in either lower or upper boundary of confidence interval is exactly the new value. So 95% correspond to p, to the judgment whether p is less than 0.05 or not. Okay. And if you are using 90% confidence interval, then including the new value in the confidence interval, you know the p-value would be less than 0.1 instead of 0.05. So that's how these two numbers are linked. And so by now, you might be wondering, well, if we can do hypothesis testing with only confidence interval, we don't really need to show p-value. And that is true. And if I had to choose either, and I would choose to put the confidence interval. Usually, conventionally, the people do put the both next to each other. And please do not do the following and showing only p-value. Okay, that is a worst practice. I'm okay if you only show confidence interval or both, but I'm not okay if you show only p-value, because there is information you can get with confidence interval, but you can't really get from p-value. Okay, so let me explain what is the information we can get with confidence interval but not from p-value. And ABCD is showing 4 different confidence intervals. Okay? In the situation, we're comparing mean difference between 2 groups, so the mean difference is 0. And since A and B include 0, so you conclude p-value is greater than 0.05, and C and D exclude 0, and therefore you conclude p-value must be less than 0.05. Okay? And there is actually difference between A and B and also C and D, although they A and B show the same p-value, and C and D also show the same p-value. Okay? And A, confidence interval very narrow, and but it includes 0 because center value of confidence interval is 0. So what is the situation when you have a narrow confidence interval? In confidence interval, okay, here's the formula for confidence interval: mean plus minus 2 times SE. And SE you can compute if you have seen the video for SE, and you know SE is written as ST over square root of sample size. So therefore, okay, so A, you know, mean is very close to 0, although sample size is very large, therefore confidence interval very narrow. Okay, but it did not result in significant difference because mean is very close to 0. So increasing sample size does not really help to exclude 0 from confidence interval. But in B, you know, mean effect is large, which may be clinically meaningful, although you didn't detect that because N is very small. That's why you have very wide confidence interval. Okay, so in A, confidence interval could be as narrow as 0.5 days to plus 0.5 days, but B could be as wide as 0.5 and to let's say 50. Okay, so middle value could be as large as 25. So in B, you know, it's a negative study, although if you include a little bit more patient, if you add few or more patient, and you might be able to make confidence interval a bit narrower so that it excludes the no value, therefore it becomes statistically significant. In C and D, it's already excluding a 0, so already significant difference, and you don't have to worry too much, but you can still tell the sample size is large or small, and what is, in the case of D, confidence interval is very wide, but it still excludes the no value because the difference was already large. Right? So these are the informations you cannot really get from p-value because the p-value, everything is all mixed into just one number. Okay? Whereas confidence interval, and you can actually get much more information. So here is a real-life example, and this is a study, one of the studies I was lucky enough to publish in New England Journal of Medicine, and looking at whether the coronary artery calcification is a risk factor for SLE. Okay. And so look at table 3. In table 3, and we were interested in looking at what are the factors associating to calcification within the patient with SLE. And so I picked 2 independent variables. So look at diastolic blood pressure. And p-value is very large, so we know this variable is not much promising. And when you look at the confidence interval, okay, and that's include the null value of 1. Again, it's odds ratio, so the null value of ratio is 1. And so that's one case, right? The another case, creatinine. P-value is greater than 0.05. It's not significant, and although confidence interval is so large. Okay. And middle value is 3.96. Okay. And here, diastolic blood pressure, and right in middle is ratio of 1, and then confidence interval is narrower, right? So which variable do you think is promising? You could detect statistical significance if you increase a little more patient, and that is this case, right? Because increasing a patient, diastolic blood pressure, and you can make confidence interval narrower, but then center would be 1. So you won't be able to exclude 1 from the interval. Although in the creatinine, if you add a few more patients, and then confidence interval might easily exclude 1, and so it becomes significant. Okay. So for your future study, and you might still want to look at the creatinine, but you probably don't look at diastolic blood pressure. All right, this is the final slide. Confidence interval is extremely important when you're trying to show equivalence. Okay, and typically in hypothesis testing, and we show difference, but there are studies we want to show equivalence. And for example, you are trying to have a new generic drug approved, and you need to show the generic drug is equivalent with existing drug. And in that case, you try to show statistical equivalence, not the difference. Okay. And many people actually used p-value for the judgment of equivalent. And if you use p greater than 0.05 as evidence of equivalent, and you are wrong. Why is that? Because having a large p-value is easy, and you just reduce sample size. So let's do the sample size of sample size of 3. Okay, and of course, and you have big confidence interval, and that probably include the null value, and p-value would be greater than 0.05. Do you really know the scenario B? Okay, so this one, scenario B is p-value greater than 0.05, but you can't really tell the difference is either 3 or 0 or 6, and so you just don't have evidence to judge difference. So that's not the same as equivalence. But in A, okay, and you have a narrow enough confidence interval, and the center value is 0. So therefore, you can see estimation is pretty good for A. So therefore, okay, and with A, you might use evidence for equivalence. Okay. So typically, okay, study showing equivalence, you never use p-value, but you use confidence interval. And you want scenario like this. Confidence interval is narrow enough and still include the null value. And what you actually have to do is you set equivalence margin before you collect data in this case. Okay, so this is a scenario, and you are trying to show bioequivalence between two drugs, and such as you're comparing mean Cmax or AUC between two groups. Okay, and you tend to look at the ratio, not the mean difference. So the margin of equivalence, and we typically set 0.8 to 1.25. What does it mean? Okay, so if you set the mean of AUC of control drug is 1, okay, and newly developed generic drug, and the difference is 20% less. That's what 0.8 means. And 1.25 means newly developed generic drug have mean AUC 25% greater than the mean AUC of control drug. Okay, so this is equivalence margin we often use for bioequivalence study. And then, in order to prove statistical equivalence, and you have to show both lower and upper boundary of confidence interval fall within this range. Okay, so if you have confidence interval here and there, you cannot say bioequivalence. And if it's here and here, again, you cannot show equivalence. And you have to have confidence interval fall right in this a priori selected equivalence margin. Okay. And in order to do that, and you do have to have sample size small enough to have a narrower confidence interval. And then when the mean difference is closer to 0, and you have more chance to have this interval fall right within this margin. Okay, so equivalent study can require larger sample size. Okay. And this is the difference from efficacy trial when you are trying to show efficacy. Okay, in ratio, if the ratio is a null value, and all you have to do is exclude this ratio of null value ratio of 1. So even with a fewer sample size, when you have effect much larger, and you can still exclude 1. So small sample size, you could, even with small sample size, you could detect statistical difference. Okay, but not for equivalence.